All right. Small victories. We'll take them. Well, we've got Canada well represented today, that's for sure. I think we got three of you guys here, so fantastic. And then Kuldeep, of course, was at school up in Saskatchewan in the cold weather, he told me so. So I figure we got two options. We can either listen to Gareth talk today or he can explain curling to us Americans, because that's a sport we just don't understand. I've been listening to a podcast about it, but I still haven't figured it out. So
It's gonna have to be my talk because I never curled. So
all right.
I've read about it. It's strange, but okay.
Yeah, well, it's no stranger than taking a little white ball and hitting it with a club 200 yards and then chasing after it and then doing it again 17 more times. So it's all relative.
Well, that's true.
Are they rocks or stones? I sort of
Yeah.
forgot.
I went to a summer camp once where we did curling on a frozen lake, or actually it was a winter camp. And we used gallon jugs for milk and filled them with water. And they're really good, like curling stones, frozen solid.
What's the mathematical or in physics, the curl of something,
Yes, yes.
which we all had and was like, I never want to do this again.
Yeah.
Yeah, ancient history to me too. All right, I think we've got a quorum. Let's start the Thursday, November 7th version of the HamSCience Telecon. Welcome everyone. A lot of familiar faces. I don't think I need to restate our purpose today. I think I will say that we are fortunate to have Gareth Perry here to talk a little bit about VLF and whatnot. And unless somebody's got a burning issue they want to raise, I'm sure we'll have some time afterwards. But let's turn the floor over to Gareth and let him get started.
all right, afternoon and evening to everybody. Let me see if I can share this thing. All right, are you seeing it?
Yep.
And then if I hit play, are you still seeing it?
Yep.
Perfect. All right, so yeah, I was asked to give a chat about VLF emissions and seismic activity, essentially. Gary asked me to talk a bit about this, and I'll be happy to. This is an excerpt from his email he sent to me. He dug around on Google Scholar and said, "Hey, your name's on this paper. Do you want to talk about it?" And I was like, "Sure. That sounds like a great idea." So this is an abstract from the ERSI General Assembly meeting, I believe it was, and was virtual, I believe, in August 21. Unfortunately, it was virtual because I'd rather have gone to Rome to do it. But I'm a supporting author, a contributing author, if you want to call it that. The main author on this is Ashanthi Maxworth, Professor Ashanthi Maxworth at the University of Southern Maine. So a lot of she did with her group a lot of the heavy lifting on this, but I'm more than happy to kind of talk about this work because it is very interesting work, and it is I guess I don't want to say outside the norm, but it's on a topic that's interesting, that's not regularly talked about in our field, but it's interesting. And so really what it is I guess the bolded down here is that there's a significant amount of effort in the community, and a small portion of the community has been expended on investigating whether or not we can look at or see precursor signatures to seismic activity like earthquakes in space physics data sets. And so Ashanthi's paper here is on whether or not we can see this in VLF measurements from satellites. And I'll talk a bit more about specifically what satellite and kind of show some supporting papers. So I have a few slides to talk about this today. All right, so the data set that Ashanthi used was the EPOP data set. So this is EPOP. This is the Enhanced Polar Outflow Probe, that's EPOP, on board Cassiope. Cassiope is Cascade, Smallsat, and Ionospheric Polar Explorer. So it's a Canadian satellite that was launched, I think it was the first on Falcon 9, one of the first successful launches, thankfully, back in 2013. And it is still in orbit. It was launched into a 1500 by 325 kilometer polar orbit. So, 81 degrees inclination. It's more circularized now. Circularized now. I couldn't tell you what the actual orbit parameters are these days. And it was originally 3-axis stabilized. It had 4 reaction wheels to kind of keep it stabilized. You could, spin it all around and do all that stuff. But the rigors of exploring low Earth orbit, passing through, the South Atlantic anomaly, and having commercial off-the-shelf products that aren't radiation hardened has kind of taken its toll. So it kind of just hobbles along now. It slowly rotates just so it doesn't get fried and have get cooked up there. So it still operates. A lot of the instruments can operate because they required the stabilization, but the instrument we're concerned with here, the radio receiver instrument, which you probably can't see. Well, it's the RRI instrument. You see the cross dipole antenna on the front end of the spacecraft. That operates no matter what orientation you're in. It's just a digital radio receiver. And so EPOP was the suite of 8 instruments, and it was meant to study the microphysics of neutral escape or microscopic characteristics of plasma outflow, and had other science objectives, including radio wave propagation, studying HF propagation, and VLF emissions. Right. So more on RRI. This was kind of on the bottom left was this graphic that was drawn up in like the mid-90s in the Canadian community about what they wanted, like what their dream setup was, to have a spacecraft flying in the top side and then having radars or emitters in the bottom side, meaning on the ground, and flying through a rural zone and studying all this stuff. They essentially got that eventually with EPOP. So that was very successful. But the radio receiver is what we call the RRI. It's 4 3-meter monopole antennas. It's designed to study natural and artificial, so transmitters, HF transmitters, but also artificial or natural emissions, so whistlers or hiss or medium frequency emissions. I think we've had people come here and talk about before. It's a bit of a data hog. It samples at 62.5 kilohertz, and that's IQ sampling. And we're able to tune it. It does this over 30 kilohertz passband, but to 32 to 30 kilohertz. But we're able to tune it down to VLF, so down to about 10 or 20 hertz, but all the way up to 18 megahertz. So it's very flexible in that regard, very agile. And we had other special features, like we could sweep through frequencies, we could sweep through spectrum in these linear sweeps or logarithmic sweeps. It had all sorts of kind of features, which is really cool. This was very much what I would describe as a campaign satellite and a campaign instrument, meaning that it wasn't just on all the time surveying. You had to ask for time, and it had to be planned. Because we had limited onboard storage, we could only do a few downlinks a day. And so I was always kind of capped at maybe 8 minutes a day of RRI active time. So each time you'd have to like plan it. So most of my postdoc was finding reasons or ways of using RRI just to collect radio data for my future career, and knowing that I would probably be one of the only people that knows what's in there, what's in the data set. That's not true anymore because Kuldeep's around, and Kuldeep's also dug through that data set. But also just kind of filling up and knowing that, the odds of something like this going up in low Earth orbit again in the near future are very slim. So I wanted to collect as much data as I could while the spacecraft is operating. So I think I lost count, but we have well over 1,000 operations at various bands looking at HF transmitters, VLF emissions, and hiss in the auroral zone, all sorts of stuff. Okay. So here's kind of an example of some VLF emissions of the many thousands of VLF passes or observations we had with RRI. This is from January 2016. It's what we call a quick look plot. So you see 2 spectrograms here, and they correspond to the two channels on RRI, we can configure those 4 monopoles into a cross dipole configuration. And this allows us to kind of get other information from the signal. We can get polarization parameters and all that kind of stuff. And if you want more detail on how to do that, the person who has the freshest knowledge is Kuldeep and the expertise on that. But this is what it looks like down at VLF. So you can see we were looking at 0 to about 31 kilohertz there in the 2 channels. And we're looking at a pass over, looks like Nova Scotia, I think the Eastern Canada, the Northeast on the Eastern seaboard there. And we're looking at just about 2 minutes of data. But we see a lot of stuff here. The ephemeris is placed here. You can see the ephemeris on the bottom showing the time, all the coordinates. But looking at the features, we see what we would describe as VLF saucers, which is an emission you get from a beam instability in the ionosphere. So again, we're at what altitude we're at here? About just under 1,000 kilometers altitude. So you get these VLF saucers, and they get the name because they look like saucers in these time spectrograms. You also see above that this very kind of well-behaved, almost like a CW transmission. That would be a VLF transmitter. And I think I didn't quite identify which one that is, because there's a VLF transmitter in Maine, there's stuff over in England, and there's stuff in North Dakota as well. And I couldn't quite remember which one this was.
That's Gareth, that's probably NAA, 24 kilohertz.
Okay,
up
yeah.
in Maine.
Okay, there
You'd
you
be
go.
flying right over it.
So there you go. So that would be that VLF transmitter. And general rule of thumb of anytime we turn this thing on in VLF, wherever we were in the world, we usually always see somebody's VLF transmitter talking to submarines or whatever. So that's a very common feature. It's actually quite striking in this one. Below the saucers at about 8 kilohertz or just above, maybe 10 kilohertz, that looks like the lower hybrid resonance. So, which is a plasma instability resonance from plasma physics. And that's can be a very common feature as well in these observations. And then below that, there's that solid signal of, I'm not quite sure what that is. And I don't trust it. And this is because this was in the early days of operating this instrument, and we were kind of getting some of the kinks out. And I think we realized shortly after this that we were tuning it not to the best optimum frequency. And so we were getting some aliasing, and we didn't know how to deal with it. So suffice to say is I wouldn't trust any of that stuff below 8 kilohertz. But this is, a nice example of all the fun stuff we can see with VLF. And there's a lot of different physics here. There's a lot of different science that can be done. I know Jonathan Rizzo gave a talk, I can't remember how long ago, excellent talk about something I'm going to show in a few minutes about whistlers. So we've seen some of this VLF science before in this community. It's a really kind of a rich area.
By the way, Gareth, right at the bottom there, it mentions NAA transmitter.
Oh, does it?
Yes,
Oh, it does.
under experiment.
There you go. They updated these quick look plots, so I'm not as familiar as I used to be with them. Okay, thanks. So here's a really nice one too. And this is what I was alluding to with Jonathan Rizzo talking about whistlers. This is a really nice example of a few that I kind of just pulled out by looking at the data over the last few days, just kind of going down a rabbit hole looking at these data. Again, it looks like we have at just sub 10 kilohertz there, you have a nice lower hybrid resonance line. I suspect that's what that looks like to me. But you have what looks like a classic signature of whistlers going on. This is a pass in, I guess, the Indian Ocean, the southern part of the Indian Ocean. I would identify that, my geography. And then it's very short again, it's about 2 minutes long. I looked at this and I was actually really excited by it because I could swear I see some some periodicity to those whistlers. So I don't know if there's some bouncing effect happening here, bouncing between the magnetic conjugate points or not, but it's a really kind of a nice example of some other classic, I would call it VLF signatures that we can study with RRI from the vantage point of low Earth orbit. You know, in this experiment, we're up at about 550, 600 kilometers altitude over the 2 minutes. And then, you know, Jonathan talked about doing the same, but from VLF receivers on the ground and whistlers and spherics and all that good stuff. And again, this is very much a very rich topic in terms of natural radio emissions from the magnetosphere that we can study. Okay, so let's get to the, I guess, the punchline of that paper, which was relating VLF emissions to seismic activity. And to kind of give a bit of a background to what Professor Maxworth was up to, I found a good paper to kind of help perhaps describe the basis of these kind of measurements. So there, as I said, there's quite a bit of literature on VLF emissions or natural radio emissions measured in space and using and linking them to seismic activity. And one of the experiments that has been done, or some of the studies that have been done is like this one, using the Demeter satellite. This is a low Earth orbit satellite. It was a French satellite. I think there was some US DoD components to it as well. But nevertheless, it was able to look at VLF emissions in a much more conservative fashion, such that it could do these long surveys of VLF emissions and do these nice studies. It was able to, I think, do onboard processing where it wouldn't have to hold on to, you know, all that, you know, megabytes of IQ data. And so one of the ways it's kind of, one of the techniques it uses is it looks at VLF transmitters, and it looks at the signatures of those transmissions to those VLF transmitters at the magnetic conjugate point. So on the bottom right of this slide, you see you're looking at spectral density of a VLF emission at a certain band. This is from 14.8 to 14.87 kilohertz to 14.89 kilohertz. It's a fairly narrow band. And in the northern hemisphere, you kind of see these hot spots of this spectral emission from this survey from Demeter. And it's a winter day, and I honestly I forgot to double check how long this was collected over. But you can see these hot spots over, looks like China, North Dakota, I think it's Turkey or Russia, and then obviously another one over Russia. And those would be those VLF transmitters at those locations. But also in the southern hemisphere, you see kind of a conjugate signal. You do see a conjugate signature. And this is the signatures picked up by the satellite on the other end of the magnetic field line. So the idea here is that these VLF missions conduct along the magnetic field line, and they can be received on the other end by your receiver on board your satellite. Now, there's some specifics here about the propagation. It really depends on what the transmitting frequency is and what the lower hybrid resonance frequency is. So if your transmission is greater than the local hybrid resonance frequency at the point of the satellite, then you can receive that signal, right? So it can propagate, that signal can propagate through the plasma down to your spacecraft receiver. But if the opposite happens, if your transmission frequency isn't high enough, it'll get reflected back. So you'll have this reflection back at that conjugate point, and you won't necessarily receive it at the satellite at your receiver. So this is kind of very similar, analogous to with HF, for example, on the bottom side ionosphere. If your transmitting frequency is above the critical frequency, your signal can pierce right through the ionosphere and go on to be received by, you know, aliens in millions of years. But if it's below the critical frequency, you get internal reflection. So the critical frequency here, the lower hybrid resonance is playing the part of the critical frequency here. And I have just two equations, I think, in this presentation, and they're there in the blue boxes. The one on the left is an equation describing what goes into the lower hybrid resonance. And then the key term to look out for is that M sub F. That's effective mass. It's the effective mass of the charged particles of the ion constituents in the vicinity in the plasma. And on the right is the actual what that's equivalent to. It's it's a sum of the chemistry of the ions. But the key is that the lower hybrid resonance, that critical frequency, is very sensitive to the chemical composition, to the ion composition in the vicinity of the spacecraft. And so the idea here is that if you have alterations in that makeup of the ions, then you will have alterations in the lower hybrid resonance. And if you have this continuous transmission, say from the northern hemisphere and you're in the southern hemisphere, any variations in what you're receiving can be linked to the change in the ion constituents in the local environment. And how do you change those ion constituents? Well, the idea here is that, well, you can do it a few ways, but one of the ways is you can get disturbances from below. And this study looked at these variations in the reception of the VLF transmitters in the northern hemisphere. So they were looking at times when your VLF transmission was dropping out, or you had these significant changes in the phase. But they were doing correlation studies to seismic activity below that point, below the reception point, and they found a strong correlation. And this isn't the only study. There's been several studies where they're seeing these kind of correlations happening between seismic activity and these dropouts in the VLF transmissions. And you can go down a rabbit hole of what might be causing that. There's I can't remember the name of it, but there's phenomena where you can get electrostatic wave production just by fracturing large amounts of rock or plate tectonics, and also I think just upheaval of mass of land or even ocean water can be propagated up to the ionosphere. There's been a lot of work done with the tsunami that was in Japan a while ago. I think it was was it 2014? It was at Sendai, I believe. And signatures were seen in total electron content of that tidal wave, of the shock wave of the earthquake, but also the tidal wave and its effects. So there is connections between what's happening, I guess, in the lithosphere, if that's the correct term, and the ocean surface, and propagating up to the ionosphere. So, when you have a giant earthquake or a large seismic activity, it's not out of the realm of possibilities that you can perhaps see a signature up at ionospheric heights, up at 500 kilometers because of that. Okay, so really what the plots on the right here are showing the VLF transmitters and the conjugate locations, but also on the top is for the same survey what the lower hybrid resonance is, and kind of representing how it varies. And this paper has a few more plots showing summer, and different variations. But really, it's that the key concept here is that any variations in your receiving power or phase of your signal from the VLF transmitters at the other conjugate point is a function of, assuming those transmitters are very well behaved and steady on, which they usually are, is a function of the local ion composition. And if there's disturbances there, that means you could have disturbances from below. All right. So now on to what Professor Maxworth was up to. So she kind of looked at this idea and didn't necessarily restrict themselves to VLF transmitters. But what they did is said, if I look at EPOP, and because EPOP RI doesn't have these giant surveys, it generally has collections that are very constrained to the North American sector and specifically the Canadian sector. And there's a reason for that, because EPOP's a Canadian satellite. We were Canadian scientists, and we know where our bread is buttered, right? There's no point in doing it on the other side of the world. We better take surveys of the Canadian sector. So we did quite a bit of surveys of the Alaskan sector, Canadian sector, And Professor Maxwell said, well, the Alaskan sector is very seismically active. We have a lot of data. So what if I just look through the EPOP data set and identify times when the lower hybrid resonance looks very disturbed or the VLF missions looks very disturbed, and see if there's a correlation between those instances and seismic activity. So in a way, they're just essentially kind of bypassing the requirement of the VLF transmitter at the conjugate point. They're just saying, well, what if I just look at just the VLF emissions, the natural VLF emissions themselves? And so this is the region of interest they identified here. And they looked at the data. So they looked at a select set of events from EPOP through 2014 to 2020. And essentially they did some comparative studies, some correlative studies to see if there was anything there to be that was of interest, anything that seemed feasible. Oh, did I forget? Oh, I did forget. Oh, sorry. I forgot to drop in one of the examples of the spectrograms. Hold on a second. Let me see if I can pull that up. I had a spectrogram of an example. Give me 2 seconds. Yes. So what if I did this? Share and also share. Right, so you should see another spectrogram here. So this is a pass that Professor Maxwell identified. This is through the Alaskan sector. You can see part of the ground track in the top left corner of the globe there, that projection. And we're looking at 4 minutes of data, and you can see quite a few whistlers. You can see a lower hybrid resonance, but you get into here from about 1429 into 1431, and you see what's described as being very turbulent, or a very busy lower hybrid resonance kind of gets scrambled, it gets enhanced. There's a lot of noise happening in this region. And so these types of signatures is what Professor Maxwell was kind of identifying is, and when I look at all these little 2 or 3 minute chunks, do I see times where all of a sudden things just get enhanced over a particular region? And then if so, is there a seismic activity correlated with that? And this is just one example of what they looked at. And so they did a survey just by manually, not in an automated fashion. And they had looked at events that were, and they did a temporal comparison or correlation. And really what they were looking for is whenever an event happened within about 1,000 kilometers of what they would consider a seismic event. And so they kind of did this temporal relation plot, I guess you could call it. On the left here, we have 24 hours along the vertical axis, and all these events in 2014, at least, along the horizontal axis. And the red stars show when they have a VLF event observed by RRI, so that they said that looks like an enhanced VLF emission, or there's a lot more turbulent signatures. And then the circles are when you have a seismic event within that 1,000 kilometers. And so they kind of did this quick survey, and they looked at these events, and they kind of realized that, yeah, you do have some events that are observed before and after seismic events. Some are happening before seismic events. They're happening in relation to seismic events. So it's a very kind of first pass correlative analysis that kind of showed some promise. Now, keep in mind, there's a lot of aspects of this that need to be tightened up as well, right? Because we have to consider how the probability of seeing an event, the probability of a seismic event, the probability of the actual
Jim needs to mute his microphone.
satellite actually being active and having it's not on all the time, that kind of thing. but they found some what they considered some promising correlation studies. And all right, and one thing they actually also did to consider, another consideration is, because it is natural radio emissions, you have to consider auroral activity. And if you're in the Alaskan sector, you're near the auroral oval. So some of these enhancements could be due to auroral activity. And so they did find that, some of these events preceded auroral activity in terms of KP index or geomagnetic storms, but other times it was during geomagnetically quiet events. And so really the end of this, not the end of the work, but where the work left off was, hey, there's probably something here to dig after a little bit more to see if there is still something. But it's something to consider is that tact of not only looking at points where we have emissions due to VLF transmitters, but maybe we can actually look at VLF emissions themselves as a route for looking for precursors or signatures of seismic activity. Right. So that was that work that Professor Maxworth did. And I haven't spoke with her for a few years. Actually, the last time I saw her, I was up in Alaska with her at HARP, and she was, training a bunch of undergrad students. And I don't know if they kept on with this project or they kind of shelved it while they focused on their teaching studies, because they're a well-regarded teacher as well. But kind of bringing it back to the HamSci connection, I mean, the deployment of VLF receivers is very much on the map and on the menu. And I guess the idea of, can this science potentially be done, with VLF receivers on the ground? And to me, I don't see why not, because that whole notion of the propagation conditions, if you have a receiver in space as looking at, say, a VLF transmitter, as opposed to a receiver on the ground, there is a bit of difference, but it's not terribly different. And so the only problem, though, is that if you remember that map I showed, all the VLF transmitters, not all of them, but a lot of them are in the northern hemisphere. There are some in the southern hemisphere. So the conjugate points would be in the southern hemisphere. So actually, if I went back and showed you that plot, if the panel B there in the bottom right, all the conjugate points, there's one. So maybe Australia would be a place to put these VLF receivers, but there's not a lot of land at those latitudes where you see a lot of the activity due to the conjugate points. The other aspect is I know they have also a VLF transmitter in Australia. So that's something to contend with. But whether or not this specific, I think we would have to dig a little bit further if this would be a potential science target for VLF transmitters or receivers rather with HamSci. But I think it's worth kind of looking at. Nevertheless, I know, as Jonathan has talked about before, and he's made the case, at least in my view, just having VLF receivers collecting data is great science in of itself. There's still a lot of, we don't know what's going on in terms of the VLF emissions, the source. Jonathan talked about whistlers, which are a very valuable resource. I mean, I think features of the inner magnetosphere, such as the plasma pods, were discovered by Whistler mode propagation, by studying Whistler modes and Whistler waves. So it's a very useful and critical remote sensing tool of the plasmasphere and the nearest geospace. So that in of itself, I think is worth deploying these things and collecting as much data as possible. And the physics of that is studying whistlers and plasma. That's I would call that more on the pure side of plasma physics, which is a great science to be studying and a great contribution to the greater science community. So the more the merrier is my philosophy on that. But yeah, that's what I had for this. I had just that 11 slides. So I'll leave it at that. And if there are any questions, I'll try my best to answer them.
Gareth, this is David. I'm wondering how many spacecraft have VLF experiments on them?
That's a great question. So I don't know the exact answer to that. Not many spacecraft have like digital radio receivers on them like this. There are some that are planned. Like I know Phil Erickson and Jim LaBelle have a CubeSat called, I think it's called Aero Vista.
Yeah, Aerovista.
And Demeter
involved
had
with that.
something. But a lot of other spacecraft, think RBSP had something on there too. But those are more to study like waves in the magnetosphere, not necessarily to study VLF transmissions or anything like that. But it's
Well, I can say that Aerovista, having been connected with it, I think it was on in limbo for a while. I think it may have restarted, but yeah, it was supposed to be picking up auroral emissions, but also capable of picking up emissions from the ground.
yeah. Yeah.
I'll also say that we've flown a rocket with a VLF experiment on it. I was involved with Viper, which was flown from Wallops, and our primary signal of interest was NAA.
Yeah, so there are a few, but there's not that many. I expect there are more out there probably on the military DoD side of things, but in terms of, civilian controlled, there's not many data sets. So and that's why I mean Demeter is a big data set, but RRI is also a fairly beefy data set for studying VLF emissions. And that's why we turned it on as much as we could because we knew there's not much of this data. So
I have a question.
yes.
I there's a lot of reentries, especially of the SpaceX satellites. I actually track. I have a website that I monitor that tracks reentries, and I noticed in one of your formulas the amount of ions in the area was a major factor. The MEFF. Um, uh, uh, thing there. And I wanted to ask about the order of magnitude of ions coming up from rocks on the ground versus disintegrating satellites re-entering the atmosphere. And
Right.
that also leads to an interesting thing because there are so many reentries now that if we have old data, we could compare old data with current data with regard to the number of reentries and the amount of metal ions that are created by that.
Yeah.
Over to you.
That's a good observation. I don't know what the order of magnitude would be, but I would expect something like a reentry would be in the vicinity of your an RRI or VLF receiver. A receiver would be significantly higher than seismic activity. But I wouldn't know the exact magnitude. But you do bring up a good point, an interesting point, and it's that that drastic change in composition and how carrying a signature, and so a colleague of mine and Nathaniel knows as well, and I'm sure a few other names is Paul Bernhardt. He's at the University of Alaska Fairbanks now, but he used to be with the NRL, and he's made a career out of looking at VLF emissions in space and how they're modified when you change the chemical composition in the region. And so one of the things he used to do was actually look at VLF emissions and the chemistry composition changes when you'd have water dumps from like the space shuttle. He's done stuff with EPOP, not with the space shuttle, but with Cygnus, the resupply spacecraft up to the ISS, and they would do a burn in the general vicinity of EPOP, and you could study the chemical changes by looking at VLF emissions and how their amplitudes would change, or like the parameters like lower hybrid resonance. And another thing that in the kind of context of reentry that can be done by looking at VLF emissions is the in the VLF range is the plasma wakes of spacecraft passing near the receiver. So another project that Paul did was he was detecting spacecraft passing near EPOP by looking at the VLF spectra, by looking at the emissions or the emissions of the plasma turbulence caused by these spacecraft moving in the vicinity. And it was kind of a proof of concept study that was a spatial awareness study. Essentially, it could complement ground-based resources in detecting spacecraft and all that kind of stuff. So, so yeah, it kind of reminded me of like there's that beyond like the looking at VLF transmission for seismic activity. There's a very rich topic of looking at other imprints of satellites moving by or stuff like that by studying the VLF emissions.
So I have a couple of questions. One is for Ed. How often do these satellite reentries disintegrate in the atmosphere? Every day, every week, every month? What is it now?
Right now, it's several times a day. And I can give you the website that tracks the reentries if you want it.
I would think that would be interesting. Yeah,
Let me,
several a day. Good Lord. And so this is not necessarily much the satellite, but all its motors and stuff like that that got it set up.
well, for these satellites, most of them disintegrate in the upper atmosphere. So if you take the weight of the metal and the fact that it is, completely disintegrated into essentially ions, there's actually a fair amount of ionization that's taking place.
Huh. Okay, so that's interesting. The second question is, we have meteor showers and they deposit metal ions.
Exactly.
They come through. So those are like once a month. What else you got?
Yeah, that's a good point.
Do they see the meteor showers?
Right now, I'm digging up that website. I'll post it in the chat.
Okay. So Gareth, did your EPOP thing see the meteor shower effect?
I never looked, but there may be an effect, but I guess it's more depending on the local effect of the lower hybrid resonance at the point of the receiver. And I would expect the meteor showers to deposit their metal much lower down, but it's still something whizzing past in the vicinity at a incredible speed. So I presume it would leave some sort of a signature. Yeah, I've never looked, and that's an interesting question. And I don't know if anybody else has looked.
And we know when they happen.
Yeah, exactly.
And they have a time signature too. It's mostly at dawn.
That's right. Yeah,
Interesting.
it's a good question.
There was the author of VLFRX tools, Paul Nicholson. He did some analysis on a VLF transmitter and meteors, and he found that he was able to detect a very minute effect using VLF transmitters. And it was interesting because is that normally it's very difficult to do, and he had to get the geometry right, but he was able to come up with something. And I can put that link in the chat. He did a full analysis, so I could put that link in the chat.
That would be good. And then next week, Gary should send these things out to us, right?
Yeah, and I see Scott Newell also just put up the EPOP database. I should have done that. Thank you. Here's where you can go look at the data and the thousands of quick look plots we have in RRI. And EPOP also had an auroral imager, so there's movies of the aurora, but from above, and all this kind of cool stuff too. So.
I'm still getting wrapping my head around the fact that you get between 2 and 8 minutes of data. And that's the data set you've got to work with compared to what I've been watching HamSCience do, where we've got so much data that's running from literally
Yep.
dozens of stations, 24 hours a day, 7 days a week, so on and so forth. It's just a different scope. That's all. It's
Yeah, yeah. I mean, originally, so yeah, of course, like as the way spacecraft goes, EPOP and Cassiope were designed back in the late 90s, early aughts of the early part of the century. And one of the spacecraft had kind of two purposes. One was to study, space physics and study the ionosphere. The other one was a tech demo of being a data courier. The idea is you'd have like a ship out in the ocean that would transmit up to the spacecraft. It would store this data. It would fly, north or something like that, and then it would downlink over land. And that was the tech demo. And of course, by the time the spacecraft got built, it got delayed, and then, SpaceX did their thing and they shot it up into orbit. The internet and what connectivity had like surpassed it. So it was essentially completely redundant. But unfortunately, we weren't able to use that connection to downlink huge swaths of data. So all we had was like this S-band downlink, and we all had funding for like 1 pass a day, 2 passes a day. When the European Space Agency started funding the operations, we could do 4 a day. So we really started piling it on. But you can do a lot of science with just a few minutes. I mean, Nathaniel and I did that field day experiment, and we got a paper out of it, and that was 2 minutes of data. So you can do quite a bit. And that was with our.
And look at what Gwyn did last week too. He just looked at such a very small amount of data.
Yep.
That was a really nice talk, Gareth.
Thank you. Thanks for having me.
Yeah.
Oh, thank you.
Oh, that was wonderful
I think
too.
it's really, yeah. I asked. I know Jonathan Rizzo. You're on here. You have to tell us your thoughts about this talk.
So I absolutely loved it. There were a lot of interesting things covered, but I do apologize for joining late because I got home from work. This science kind of reminds me of something that I've heard quite frequently in the VLF community. It called Earthquake paper written a while ago. I believe it was in the 70s from a researcher in Japan. And he detected VLF emissions at around 81 kilohertz before earthquakes would occur. This was local. These were local emissions, and not many people have been able to kind of follow this science, but others could. This is obviously I'm not really sure if in this case it's related, but this is actually very interesting science. And there was a fellow who I was helping out last year, who I was helping him with his data collection system, and he was able to, and I don't know how that he did this, but he was able to correlate. He was able to correlate. It was either ELF data or VLF data, emissions correlating with seismic events, local seismic events. And when we were first talking, I just couldn't really believe it, because the two seem very unrelated to me, but it turns out that they're not. And so this brings these sorts of studies are very useful to understand how interrelated seismic activity with VLF with VLF emissions, and what are the mechanisms that actually drive these emissions. I still can't really answer that because I don't know, but this kind of brings us closer. Gareth, I'll be watching the beginning part of the presentation
Sure.
on YouTube, and I do apologize for missing that, but I really did enjoy it, and I also thank you for your support of the ground-based VLF receivers. It's been very exciting with the receiver that I use, that me and Nathaniel put together and installed. It's been collecting a lot of good data, and with a network of VLF receivers, I hope that that the data could be used to shed more light on this topic. Just as Garrett said, there's very good science value in VLF VLF receivers collecting data continuously, like mine is. So it's this is something that I'm really excited about, and I definitely hope to answer some more questions with this.
Right.
But I do have that link, and I'm going to post it in the chat.
Perfect.
There regarding a meteor that was first seen visually, and Paul did the analysis using a VLF transmitter. So the link to it is in the chat, and he did some really nice analysis.
Right. Thank you.
Mm-hmm.
I have to run in a minute to dinner, but I want to make sure that I want to introduce, many of you know her already, but some of you do not. Dr. Kukai Hazumi. She's joining us today. She's our HamSci postdoc here at Scranton. So we have not one, but 2 HamSci postdocs, which is really amazing. So Kukai is the HamSci postdoc at Scranton. Kuldeep is the HamSci postdoc at NJIT. So everyone just say hi to Kukai, and we'll be looking forward to hearing from her more in the upcoming Telecon.
Hi,
Welcome, good to
everyone.
have you
It's
here.
me.
There she is. Okay.
Yeah, it's me. Thank you for having me as a HamSci postdoc.
So I didn't want to, with that statement that I made, I didn't want to poo-poo the possibility of an interaction here. I do want us to keep our eyes wide open for what, all the different related aspects of it, because I think this is really interesting research.
So I have a question for Nathaniel or anybody else. What is
Yes.
what is the possible physics for getting an earthquake signal on the ground, not a volcano, just an earthquake, up to the ionosphere or to the VLF?
So there's 2 that I can think of. The one is just the fact that if you're wiggling, if the ground is wiggling, it's going to cause some sort of a disturbance in the medium in the neutral atmosphere that can propagate up to the and couple to the ionosphere, and then you can get that causing some chemistry changes or some variability in density, in the plasma density at the top side ionosphere.
You're thinking of just a small pressure wave.
Yeah, exactly. And we know we've seen this
And
before.
I'm not going to.
What's that?
I also going to say, I know that there are some papers out there, or I believe there are some papers out there, I can probably find them, that talk about like if you have like some sort of, I think, ferromagnetic or there's some sort of electromagnetic thing that people claim as well. So
Yeah,
I think I'm not prepared to talk about the details about that. I just know that some people talk about these things.
there's a name for it, and I can't remember what it is, but it's like, yeah, it's a electrostatic, electromagnetic signal that can be generated by fracturing rock or something like that. The thing I always think about is, those breath mints that you can chew and crunch down and they cause light to go off.
Yeah.
It's like that, but like fracturing of you know, the rock, and then it can cause an EMP pulse or whatever it is, and it can go up and that
Piezoelectric
can be detected.
effect.
Yeah, like a piezoelectric effect. Yeah, there's an actual name for it, and it's buried in one of these papers because I read it once. But that's the two things I can think of what might cause that. But yeah,
Those are the two things I thought of too.
great minds think alike then.
Yeah. I need to say 7:30, so have a great day. But you feel free.
I
Yeah,
have
one
to go
comment,
too, so
before everyone leaves, we probably won't have a call next week. Many of us will be at the NASA Citizen Science Conference, talking to the folks that help fund some of our research and learning a little bit more about citizen science ideas we can share with them, and how things we can learn from others. So that'll be on the HamSci agenda next week. So if that's the case, it looks like we'll get together. I think the 21st of November is a good Thursday, right? I'm not sure when Thanksgiving is. Probably later.
Later.
28th.
It's
Okay,
the
it's the
following
28th.
one. 28th
Okay.
is Thanksgiving.
Okay. So I'm not sure what we'll have planned for the 21st, but hopefully we'll find something interesting. So any closing comments or anything that Mary Lou, I did save the chat, and maybe what I should do after each week's call is, once it's up on YouTube, post the YouTube link and some of the chat links and stuff.
Yeah, thank
in the
you.
groups.io, and then we've got a nice record. So
Yes, great. Well, have a good
Would
trip next week, you guys.
all right. Okay, if there's nothing else, we'll call it a wrap for this week. Thank you, everyone. Good seeing everyone, and thanks for all the questions, and of course for Gareth for presenting, because I know he's got to finish the end of semester and he's got a lot of work ahead of him for the planning the HamSci conference workshop next year too.
Yep,
So
that's for
I'm glad
sure.
we're able to do this now, so, and not in the spring.
Thanks again.
So, all right,
Thank you.
73 all.
73.
Have a
Bye-bye.
great couple of weeks.
73, goodbye.
So long.